We'll wait 2 more minutes for others to join. If not, we'll start the class by 3:05 sharp. Thank you. Okay, I think we'll start now. If there are others, let them join in between as well. So, as you all know, this is Computational Fluid Dynamics course from the NPTEL. For that, we are just conducting live session every week. So in this session, we'll be solving problems associated with that week's assignment and that week's practice problems and previous week's assignments problems that you have submitted, so that you will be getting an idea of what the problems are and how to solve them in future, so that it would be helpful in your exams as well and in assignment submission as well. So let us start now. So the course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras, and myself, Ankara Kartika, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So this session happens every Saturday from 3 p.m. to 5 p.m. unless until there is a change, it will be informed priorly. So we'll start now. So today's class we'll just directly go through the problems. So as you all know, like in we have been seeing the 7 weeks problems. So this is week 7's assignment problems and related problems to that week's assignments. So basically, so this is like week 7 problem. Till now what we have seen is, first we have seen the flow through rectangular duct and triangular duct problems, and then followed by that we saw about discretization schemes and what are the governing equations. First we saw about the governing equations for the concerned system of flow, like including mass mass conservation, momentum conservation, energy conservation, and species conservation if it is involved. So after that, we saw about the discretization schemes and the stability and convergence conditions and consistency, like all those things associated with the discretization of the problems also we have covered. So now it is about solution to the Navier-Stokes equation. So in this weeks it is mostly about getting the solution for the compressible flow systems. What are all the available methods, everything. So the theory behind this is taught completely during the weekly lectures by the professor. So we'll just see how to solve the problems and what type of problems can come during the exams as well or in the assignments. So this is a case one. So in this we are seeing a figure where a fluid is entering through this and it is leaving through this particular section. So what is given in this? Compressible flow through two-dimensional expansion in a pipe of circular cross-section. So like fluid is entering through this area of a smaller cross-section and it is leaving through an area of larger cross-section. So thereby there is an considerable expansion happening in the system. So after that, what are the questions that can be asked from this? Question 1, it is about which of the following statements are correct about compressible flows? Any flow involving gas is necessarily compressible flow. Compressible flows are inviscid. So what is asked? Any flow involving gas is necessarily compressible flow. Compressible flows are inviscid. So we'll see the options first. Option A 1, option B 2, option C 1 and 2, option D neither 1 nor 2. So about the first statement, I would like to clarify that it is doesn't mean that all flows involving gas should be compressible. Here, compressible flows denote the state of the flow, not the property of the fluid that is involved in the system. So answer is neither one nor two because we cannot say that all gas flows are compressible and also we cannot say all compressible flows are inviscid. Inviscid, what does it mean? There is no change in the like there is a zero viscosity. So we'll just see how. While all flows are compressible, flows are usually treated as being incompressible when the Mach number is smaller than 0.3. Since the density change due to velocity is about 5% in that case. So what does it mean? While all flows can be compressed, flows are treated as incompressible when there is a Mach number is less than 0.3. So what happens when Mach number is less than 0.3? The density change in those systems would be less than 5% or equal to 5% in that case. So what is Mach number? Mach number is the ratio of speed of the flow to the speed of the sound in that particular system, and this is should be less than 0.3. Since the density change due to velocity is about 5% in that case. So density change can be considered as invariable, that is it is almost varying very less. So the flow is incompressible. Incompressible flows are such that we cannot we can say that density is almost constant. So 5% is acceptable domain. So what is inviscid flows? Inviscid flows assumption means physically that viscous shear and normal stresses are negligible. Thus, all of the viscous shear stress terms on the force side of the momentum equation drops out as well as normal stresses due to viscosity. So is that happening? Like it is not happening with compressible flows, right? If it is an inviscid flow, all the viscous shear stress terms on the force side of the momentum equation drops out. Like that would be equal to 0 and the flow equation would be completely changed, but it is not happening. Inviscid flow is a completely different flow. Compressible flow is here is not something else. So here we cannot say that compressible flows are inviscid flows or all gas flows are compressible flows. So both the statements are false. So answer to this is neither one nor two is the correct answer because we cannot say any flow involving gas is necessarily compressible flows and we cannot also say that compressible flows are inviscid. It is just that in most cases gas flows are compressible flows, and while it is how to define compressible flows? Compressible flows are those in which Mach number is greater than 0.3. So if it is less than zero point 0.3, the density change in those system is less than 5%. So we treat it as incompressible. Flows are usually treated as being incompressible when the Mach number is smaller than zero point 0.3. So just remember this, when Mach number is less than zero point 0.3, it is incompressible flows because density changes in those systems is 5%. 5% is a approximately negligible level. So we can say that it is not changing much. So it is an incompressible flow. Incompressible flows, there is no change in density. And what is inviscid flows? Inviscid flows means that physically all shear, viscous shear and normal stresses are negligible. So what happens in that time? All of the viscous shear stress terms on the force side of the momentum equation drops out, as well as the normal stresses due to viscosity. So thereby those terms drop out and it is a completely different phenomena happening. So compressible flows are not inviscid flows. So I think by question 1 we are clear about two aspects. Compressible flows are not inviscid flows, and compressible flows are those in which Mach number is greater than zero point 0.3. It doesn't say, only restrict itself to flows involving gas flows. We'll go to question 2 now. I hope it is clear. So in question 2, it is asked that which of the following is among the difficulties encountered in the solution of compressible flows. So the difficulties given are coupled equations, non-linearity of governing equations, determination of pressure. So my answer to this is 1 and 2. We'll see the options first. So in option A it is 1 and 2. Option B it is 2 and 3. Option C it is 1 and 3. Option D 1, 2 and 3. So answer is option A because it is asked regarding the difficulties encountered during the solution of compressible flows. In compressible flows, what equations would we have? We have mass conservation equation, that is the continuity equation, and momentum conservation equations. So in momentum conservation equation, the density terms would still be there in that coupled equation. So we call it coupled equation because it is like pressure and velocity both are present in a single equation, and thereby we cannot solve it independently. So these equations are coupled, like pressure and velocity are coupled, so it is not solved separately. Therefore, it is a difficulty encountered during the solution of compressible flows. So coupled equation is true. And second is non-linearity of governing equations. If you remember the momentum conservation equations, you would know that we would be having terms like u dou u by dou x and some like so on in the momentum conservation equations. So like we would be having dou by dou x of rho uv and dou by dou y of rho v square. Like if it is an x momentum equation, we would be having, dou by dou x of rho u square. Here we cannot take out rho because it is a compressible flow system. And the second term would be dou by dou y of rho uv. Here we are considering only two-dimensional system. So if that is the case, we are having a coupling between u and u square, u and u or u and v. So it becomes non-linear governing equation. Like they are like one factor is influencing the other in terms of the power. So we cannot like separate it, and it is a non-linearity of the governing equations when we are dealing with the compressible flows. And the third one is determination of pressure. What happens is that pressure we are determining from the equation of state, not we are not solving it from the governing equation. Rather, what we are getting from the solution of the governing equation for compressible flow system is that we would be getting rho rho u, rho v, everything. And if it is an energy equation, we would be having rho et also. But pressure is a function of I mean, it would be obtained from the equation of state. Thereby, we cannot say that it is a difficulty. Pressure and similarly temperature is as well would be determined from the equation of state. So answer is 1 and 2. Continuity equation is this: dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v is equal to 0. If it is an incompressible equation, we would be eliminating the change in density and we would have been taken it to the other side. And momentum balance equation in x direction, it is dou by dou t rho u plus dou by dou x of rho u square plus dou by dou y of rho u by, it should be square actually, I don't know. So momentum balance equation in x direction, dou by dou x of rho u square plus dou by dou x of rho u v is equal to minus dou p by dou x plus dou by dou x of 2 mu dou u by dou x plus dou by dou y of mu dou u by dou y plus mu dou v by dou x. So in the similar way for y direction, we would be having dou by dou t rho v plus dou by dou x rho u v plus dou by dou y rho v square is equal to minus dou p by dou y plus dou by dou x of mu dou u by dou x plus mu dou v by dou x. I mean, here it is one more bracket would come. And similarly, dou by dou y of 2 mu dou v by dou y. And therefore, as you can see from this particular side, the equation is coupled. The pressure term is present and velocity term is present as well. And the velocity is not linear, like it is u square uv. So there is a non-linearity of in terms of the velocity factor as well. So it is holding to the difficulty of solving coupled equation and non-linearity in these equations. Therefore, both 1 and 2 are the answer. And similarly, we'll see how continuity equation we will be solving to get rho, x direction momentum equation for rho u, y direction momentum equation for rho v, and energy equation for et. And pressure we would be getting from the equation of state, which is a function of rho and e. Similarly, temperature we would be getting as a function of rho and e. So determination of pressure in this equation, I mean in this method, is not a difficulty. Rather, we are getting it from the equation of state, whereas the only difficulties encountered are non-linearity in the governing equation and coupled equations. I hope it is clear. So solving the compressible equation is we encounter two difficulties. One is the equations are coupled and the second one is there is a non-linearity existing in those equations. So we will now go to question 3. Consider the steady compressible flow through the diffuser section of the circular pipe shown schematically in figure 7.1. So the flow may be compressible because, so here the flow is through the diffuser section of the circular pipe. The flow may be compressible because one second guys. So the option 1, fluid is a gas. Option 2, velocity is high. Option 3, pressure is high. So answer is, not answer. Options are A, option A 1, option B 2, option C 3, option D 1, 2 and 3. So the answer to this is velocity is high. So what happens with the compressible flow is that we have seen that if the Mach number is greater than zero point 0.3, it is compressible flows. What is Mach number? Mach number is the ratio between the sound of fluid in that source and, and velocity of fluid in that particular source and in that particular medium to the velocity of sound in that particular medium. So if the velocity is high, we can say it is compressible. Like velocity should be that high for it to be compressible. So answer to this problem is option 2. That is B. B is the right answer. So while all flows, again we are just repeating it, while all flows are compressible, flows are usually treated as being incompressible when Mach number is smaller than zero point 0.3. So on the other hand, Mach number greater than 0.3, it means that the flow is compressible. What is Mach number? Mach number is the ratio between speed of flow to the speed of sound in that particular medium. So use local flow velocity and see speed of sound in the medium. If velocity is high, Mach number will be large, therefore the flow will be compressible. So it is just that velocity is high. So when velocity is high, we call it Mach number would be high, and since Mach number is high, we say that it is flow is compressible. We'll go to question 4. In question 4, it is asked that consider the steady compressible flow through the diffuser section of a circular pipe shown in 7.1. So this is 7.1. If the flow is axisymmetric and viscous, then how many partial differential equations do we need to solve? How many partial differential equation need to be solved to get the flow field? So it is mentioned that it is a compressible flow and the flow is axisymmetric and viscous. So we'll see that. So option A 2, option B 3, option C 4, option D 5. So here we have that it is mentioned that the axisymmetric flow. So we are just taking it in one particular direction. So the 3-dimension is reduced to 2-dimension. So for that case, we have one continuity equation. And since now we are considering only 2-dimensional flow system, see, although there is a mention of circular pipe, it is mentioned that the flow is axisymmetric, and therefore we are considering it in a 2D plane. So here we have two momentum conservation equation, one in x direction and one in y direction. So now we have three equations, one continuity equations, two momentum conservation equations, and since the flow is compressible, we need to solve for the energy equation as well. Therefore, on the whole, we have four equations. That is one continuity equation, two momentum conservation equations, and one energy equation. Because the flow is compressible flow, we need to account for the change in energy of the system as well. So we need to solve for four equations, 4 partial differential equations. So continuity equation, x momentum equation, y momentum equation, and an energy equation. So I hope it is clear. Now we'll go to question 5. In question 5, in In question 5, it is mentioned that for the compressible flow case shown in figure 7.1, which of the following statements is true about the McCormick method? So the figure is the same from the previous slide. So here we are dealing with McCormick method. If it is used, which of the following statements are true? So the first one, it cannot be used because the flow is steady. Second, it cannot be used because the flow is viscous. Third, it cannot be used because the method can be used only for Cartesian coordinate system. Option A 1, option B 2, option C 3, option D none of the 3 is correct. So answer is option D. Because in McCormick method we can use it for steady flow system, and it can also be used to solve the viscous flow system, and similarly it can be used when there is a mention of Cartesian coordinate system as well. It does not restrict itself to any of the things that is mentioned over here. The first is like it can be used to solve for the steady flow system. Second is it can be used when there is a flow is viscous flow, and third it can be used because the method can be used for the Cartesian coordinate system as well. So all three systems given over in this particular slide are not suitable, I mean are false regarding the McCormick method. Like all these statements are false when McCormick method is considered. So answer to this question is option D, that is none of the 3 is correct is the right answer. In computational fluid dynamics, McCormick method is widely used discretization scheme for the numerical solution of hyperbolic partial differential equations. This second order finite difference method was introduced by Robert McCormick in 1969, and the McCormick method is very well suited for nonlinear equations. So obviously it is suitable for compressible flow systems and Invisit-Burger equation, Euler equation, everything. For nonlinear equations, this procedure provides the best results. So according to this, McCormick method is widely used discretization scheme for the numerical solution of hyperbolic PDEs, and it is a second order finite difference method which was introduced by Robert McCormick in 1969, and it is a very well suited method for nonlinear equations like our equation, that is from the compressible equations we would be getting the nonlinear equation, coupled equation, everything, and for nonlinear equations this procedure provides the best results. For linear equation, McCormick's scheme is equivalent to Lax-Wendorf method. So according to this, McCormick can be used for steady state system, steady flow system, and it can be used when there is a viscous flow. Third, it can be used when the system is Cartesian coordinate system as well. So now we are moving on to question 6. In question 6, it is mentioned that for the compressible flow case shown in figure 7.1, which of the following statements is true about beam warming method to find the velocity and pressure fields? Pressure is obtained by solving a Poisson equation. Although the flow is steady, we solve the unsteady form of the Navier-Stokes equation. Solution of the energy equation, since we require only pressure and velocity. Okay, so the last question was about McCormick method, and this question is about beam warming scheme. So which of the following statements is true when we use beam warming method to find the velocity and the pressure fields? So first statement, it is given that pressure is obtained by solving a Poisson equation. Actually this is false because we get the pressure equation by solving equation of state. Second, although the flow is steady, we solve the unsteady form of Navier-Stokes equation. And third, solution of the energy equation, since we require only pressure and velocity. and option A 1, option B 2, option C 3, option D none of the three is correct. Option, right answer to this problem is option B, because as we mentioned that pressure is obtained by solving a Poisson equation, it is false. While the second statement, it is mentioning that flow is steady flow system, because it is a compressible flow system and it would have been it would have attained the steady flow state, but we would be solving the unsteady form of the Navier-Stokes equation. While third statement, it is mentioning that solution of the energy equation, since we require only pressure and velocity. So again, this is false. Beam warming is an second order accurate implicit scheme, like it requires no stability condition. So it is like a unconditionally stable system. So we, in general, we would be solving for the unsteady flow system. In numerical mathematics, beam and warming scheme or beam warming implicit scheme was introduced in 1978 by Richard Beam and R.F. Warming. It is a second order accurate implicit scheme mainly used for solving nonlinear hyperbolic equations. It is not used much nowadays. Like in beam warming scheme, we would be solving for the system and there would be a system of equations which we would be using the tridiagonal form or any other mathematical representation to solve it simultaneously, like in the implicit method. So it is a second order accurate implicit scheme which is introduced by Richard Beam and R.F. Warming, and this is used for mainly for solving nonlinear hyperbolic equations, and it is not used much nowadays. So like only the second statement was right, which was mentioning that we would be using the unsteady Navier-Stokes equation to solve, whereas the first one was like we would not be obtaining pressure from the Poisson equation, and the third one, it is like solution of energy equation, since we require only pressure and velocity. Like again, it is like there is no, it is stating that we do not need it, but in actuality we need it also while solving the unsteady Navier-Stokes equations. Answer is option B. Question 7, we will now see which of the following statements is true about McCormack's scheme. First one, it is conditionally stable. Second, it cannot be used for unsteady flows. Third, it can be used only for linear equations. Fourth, it is not applicable for viscous fluids. So answer is it is conditionally stable is the only true statement, because in option B it is mentioned that it cannot be used for unsteady flows, which is again false, because in Navier-Stokes equations when we are solving for it, mostly we would be dealing with the unsteady flows. And third, it can be used only for linear equations. Again, this is false, because we are now dealing with nonlinear system of equation. And fourth one is again false, because it is not applicable for viscous flows, which is false, because in previous slides itself we have seen the answer to this. It is that McCormack's scheme can be applied to viscous fluid flow. So only left out option is it is conditionally stable. So in general, for McCormack scheme we have a conditional stability. So stability criteria for McCormack scheme, it is a stability criteria so that the time step is less than certain values. So the time step should be less than or equal to f of delta t by CFL divided by 1 plus 2 times of RE. So here f is a safety factor, it is almost equal to 0.9, and delta t CFL, it is the CFL limit. So it should be less than certain values, and RE delta is the mesh Reynolds number. So it is a minimum of U delta X by nu and V delta Y by nu. So it depends on like Reynolds number in general is rho V D by mu or mu rho V D by nu, whatever it is. So in here mesh Reynolds number states that D or that D, here it is delta X or delta Y, and similarly V velocity component is U or V. It depends on the system. Sorry, it depends on X or Y, and mostly it depends on mesh. So CFL delta T CFL is the inviscid CFL limit, and it should be less than or equal to 1 divided by U by delta X plus V by delta Y plus A times of 1 by delta X square plus 1 by delta Y square to the power of 0.5. And so it is like taking the reverse of this components and inverse of this components. And if the A is the speed of sound, I don't know from where A came. Okay, here A is there. So speed of sound in the medium. So delta T should be, the delta T is nothing but the time step in that solution process. So the time step we are choosing should be less than or equal to F times of delta T CFL divided by 1 plus 2 by RE delta. So F is a safety factor, as I have mentioned. It is around approximately 0.9, and delta T CFL is the inviscid CFL limit, which is less than or equal to 1 divided by U by delta X plus V by delta Y plus A times of 1 by delta X square plus 1 by delta Y square, and taking whole square root. And here U is the U component velocity, V is V component velocity, delta X and delta Y are mesh sizes, and A is the speed of sound in that medium, and RE delta is again given, which is the minimum of U times of U by nu delta U delta X by nu and V delta Y by nu. So it is nothing but mesh Reynolds number. So stability criteria exists for McCormack scheme, and therefore McCormack scheme is conditionally stable scheme. So that is the only true statement. It is conditionally stable, whereas it can be used for unsteady flows, and it can be used for nonlinear equations as well, and it is applicable for viscous fluid system as well. The answer is option A. We'll now go to question 8. In question 8, it is asked that which of the following statements is true about beam warming method. Option A, it allows solution by marching forward from grid point to grid point. Option B, it allows solution by marching forward in time from time step to time step. Option C, it requires intermediate evaluations in going from one time step to the next. Option D, none of the above. So we know that in solution of beam warming scheme, it is an implicit method. On that basis itself, like we can say, we have previously seen that would be solving it simultaneously. So it requires intermediate evaluations in going from one time step to the another time step. So answer is option C is the right answer. That is, it requires intermediate evaluations in going from one time step to the other. So one dimensional wave equation So if it is dou u by dou t plus alpha dou u by dou x is equal to 0. For beam forming scheme, we can write it in this form, like after discretization, uin plus 1 minus uin by delta t, and that would be equal to, or equal to minus alpha. I mean, what happened is that this delta t has gone the other side, and uin has also gone to the other side. Uin minus alpha times delta t ui, yeah, I plus 1 n minus uin by delta x. So these are the extra terms. So here, as you can see, that we are using the intermediate evaluations between the time steps by means of this. Like here we are finding it out at n plus 1th time step, and therefore we say that it requires intermediate evaluations between time steps for the McCormack scheme. Which of the following, question 9, it is asked that which of the following describes the beam warming method. Second one, explicit, second order accurate in time, second order accurate in space, conditionally stable. Option B, implicit, second order accurate in time, second order in space, and conditionally stable. Option C, implicit, first order accurate in time, second order in space, and conditionally stable. Option D, explicit, first order accurate in time, second order in space, conditionally stable. So beam warming scheme is an implicit scheme, and also we know that it is second order in space and second order in time, and also it is unconditionally stable. Like implicit scheme, so therefore it is unconditionally stable. Answer is option B, that is implicit, second order accurate in time, second order accurate in space, and unconditionally stable. We will now see beam warming scheme is a second order accurate implicit scheme mainly used for solving nonlinear hyperbolic equations. Beam warming scheme forms a tridiagonal system which we would be solving in simultaneous and tridiagonal method. This is a linear system of equations forming a tridiagonal coefficient matrix. Like after the substitution, it is a linear system of equations forming a tridiagonal coefficient matrix. So it is a unconditionally stable scheme. We are not doing any march forward or marching time stepping. So it is unconditionally stable scheme. There will still be oscillations, that is dispersion error will still be present. So beam warming scheme is second order accurate in space and second order accurate in time, and it is an implicit scheme and it is unconditionally stable scheme. So I hope we are clear on that point. So now we go to question 10. In question 10 it is asked that the advantages of beam warming method over McCormack method are: it is applicable for coupled equations, it is applicable for viscous fluids, it accounts nonlinear effects, larger time steps can be used. Answer is option D. I'll say why. So because both are like applicable for coupled equations and both are applicable for viscous fluids, and both accounts nonlinear effects. So like it is not an advantage of beam warming method over McCormick method. On the other hand, the only difference between beam warming method and McCormick method is that beam warming method is unconditionally stable while McCormick method is conditionally stable. So McCormick method, there is a criteria which fixes the time step, whereas in beam warming method there is no such criteria. Therefore the time step can be adjusted however we need. Therefore larger time steps can be used when we are using beam warming method over McCormick method. So to put it simply, we have beam warming method, we have McCormick method. So in beam warming method, it is unconditionally stable, whereas in McCormick method, it is conditionally stable. Conditional stability, we have seen two, like few slides before itself, that delta T should be less than or equal to F into delta T CFL divided by 1 plus 2 by RE delta, something like that. So there is a criteria which fixes the time step size in McCormick method. That criteria is absent in beam warming method. Therefore, the beam warming method can have larger time steps as well. So answer is option D, that is larger time steps can be used. Option D is the right answer. We'll now go, implicit methods allows you to have larger time steps. The error introduced in having larger time step, that is a truncation error, may mean that you cannot put effort to have a very large time step from an accuracy point of view. You will still have to reduce to a small time step. So what it means is, even though there is a no mention of like condition for the time step in beam warming method, still we should not be having a larger time step, because from accuracy point of view it would be reduced. However, so it should be it can be more than McCormick method, but it still cannot be the larger or largest in the space. If interest is not in time accurate solutions, we can take large time steps. So what it means, and then get to the steady state solution. So if we are not very interested about time accurate solution, that is before acquiring steady state, if in the during the unsteady state operation, if we are not even interested in the solution at every 0.1 second or every 1 second, and our primary interest is to get the solution at 1 second only, then we can take larger time steps as well. That would not be an issue over there. So that is what is mentioned. Implicit method allows you to have large time step. Error introduced in having a large time step. Truncation error may mean that you cannot put effort to have very large time step from an accuracy point of view. You will still have to reduce to a smaller time step. If solution interest is not a time accurate solution, we can take large time steps and get to the steady state solution. Like steady state solution, we can get, and if only steady state solution is fine, we can go with having that large time step as well. Now we go to question 11. In question 11, it is asked that which of the following statements is true about compressible flows? First, they do not obey Navier-Stokes equations. Second, they involve significant density changes. Option A, 1 only. Option B, 2 only. Option C, 1 and 2. Option D, neither 1 nor 2. So by now we are familiar with the answer. Thereby I give you guys 1 minute time. So just think about it. We all know the answer, to be frank. So we'll just see the answer in 1 minute. So answer is actually 2 only, because compressible flows equations obey Navier-Stokes equation as well. It is that when it is an incompressible flow, we will reduce the equation to a different form, but rather than that, they obey Navier-Stokes equation as well. But they involve significant density changes, which is what we have seen from the Mach number as well. That in if Mach number is greater than 0.3, density changes would be significantly more than 5%. So we cannot say it as incompressible. So it comes under compressible flows. So compressible flows, we have Mach number greater than 0.3 and we have density changes to be significant. So answer is option 2. Like compressible flows obey Navier-Stokes equations, whereas they involve significant density changes also. So answer is option B. Now we'll go to question 12. In question 12, it is asked that in compressible flows, density is obtained from which equation? Equation of state for the fluid, energy balance equation, 1 only, 2 only, 1 and 2, neither 1 nor 2. Actually, neither 1 nor 2 is the right answer, because here we are dealing about density. So we are in question, it is asked that from which of the following equations density is obtained in compressible flows. So in compressible flows, we solve 4 equations for if it is a two-dimensional system. So first is continuity equation, second is x momentum equation, y momentum equation, and energy equation. So from the energy equations we get Et, and x momentum we have rho u, and y momentum we have rho v, and from continuity equation we get rho, whereas from the equation of state we get pressure and temperature. So answer is, we are not getting from equation of state and we are not getting from energy balance equation as well. So answer is neither 1 nor 2. So we'll go to question 13. In question 13, it is asked that which of the following can be considered as compressible flows? A racing car traveling at a top speed of 360 km per hour and a passenger aircraft traveling at a cruising speed of 700 km per hour. So option A 1 only, option B 2 only, option C 1 and 2, option D neither 1 nor 2. So I'll give you guys 1 minute time. So please pick out the right answer from the options and we'll discuss why. So basically, in this, both are actually compressible flows because their velocity is quite high, and we need to identify if it is falling under our criteria, because it is, imagine a racing car traveling at 360 kilometer per hour. That would be so high velocity. And similarly, passenger aircraft traveling at 700 kilometers per hour. See, both of 360 and 700 are very high, so both are actually compressible flows only. So answer is C, that is both 1 and 2. So we'll just see how that is. So Mach number is given by U by C. U is the local flow velocity and C is the speed of sound in the medium. So both are in air. So speed of sound is 343 meter 343 meter per second, and therefore the first one is 360 kilometer per hour. So U is 360 into, we are converting into meter per second, which is 100 meter per second. We are getting the Mach number as 0.29, which is approximately zero point 0.3. So we can say it is the compressible flows, because it is, if it is greater than or equal to 0.3, we say it is compressible flows. And second, it is 700 kilometer per hour. Again, if we convert it into meter per second, we are getting it as 194.44 meter per second. Imagine it would be that fast. So again, it is a compressible flow because the velocity is very high. So Mach number is obviously greater than zero point 0.3 here. It is 0.56. So we can say it is compressible. Mach number greater than 0.3, it is compressible. Mach number less than 0.3, it is incompressible. For Mach number to be greater than 0.3, velocity should be very high. So here it is very high velocity. So both the options, that is racing car and passenger aircraft, both are traveling at a very high speed. Therefore, both 1 and 2 are the right answer. So actually we'll take a 5 minutes break before we come up and continue the session. We'll come back now. The time is 4:01, so we'll come back by 4:06. Thank you. Okay, there is some internet disturbance. So I'll just rejoin again. Yeah, sorry for the trouble. If anyone was disconnected during the time, please let me know. I don't think so, but yeah, I'll share the screen again. Like during some internet disturbance has occurred. So now we'll start. So we saw about how we classify the flows as compressible based on the Mach number. So for that we have seen with an example as well, where if we get Mach number greater than or equal to 0.3, we call it as a compressible flows. Flows are usually treated as being incompressible when Mach number is smaller than 0.3. I think we can modify the statement by now. Flows are treated as compressible when Mach number is greater than 0.3. So that's it. Now we'll go to question 14. In question 14, what is asked? Which of the following statements is true about McCormick scheme? It is conditionally stable. It is first order accurate. 1 only. 2 only. 1 and 2. Neither 1 nor 2. So answer is option A, because both McCormick scheme and beam warming scheme are second order accurate. But the only difference is that in McCormick scheme it is conditionally stable, whereas in beam warming scheme it was unconditionally stable. So for this question the answer is it is conditionally stable. Now we go to question 15. In question 15 it is asked that solution of nonlinear equations is rendered difficult by which of the following factors? They need iterative solution. There is no guarantee of convergence. Option 3, solution may depend on initial guess. Option A, 1 only. Option B, 1 and 2. Option C, 1 and 3. Option D, 1, 2 and 3. So the question is solution of nonlinear equations is rendered difficult by which of the following factors? So till now we have seen about the equation being nonlinear and it was posing difficulty. So in what way it is difficult? So first option it is they need iterative solution, and second one there is no guarantee of convergence, and third solution may depend on initial guess. All three are right actually. So answer is option D, because the equations we were solving by iterative methods mostly, and there is no guarantee of convergence, like it may or may not. All these are like cat on the wall, and like we can try ways to reduce the chances of not getting converged, but we cannot always be it cannot always be perfect. So there are times when you would be needing the converged solution, and it would be like always getting in like not getting converged, and the solution depends on initial guess. Sometimes it do happen, because if you give a far away guess, imagine it would be like going in the loop and the solution would be getting diverged. Yeah, diverged, that was a word I was looking for. So there is no guarantee of convergence, there are high chances for divergence. So we'll go to question 16. In question 16, which of the following statements is true about the nonlinearity in the context of governing equations for fluid flows? Multiple variable appear in same equation, and variable appears in nonlinear form in one or more equation. Source terms can cause nonlinearity in the fluid flow. Option A, 1 only. Option B, 2 only. Option C, 1 and 2. Option D, 2 and 3. So option D is the right answer, because what do we say with nonlinearity? it was about not about appearance of multiple variables in the same equation, that is like coupling, but in nonlinearity the same term appears in nonlinear form in one or more equations. For example, in the momentum conservation equation, if you remember, you have the terms like u square, uv for the x momentum conservation equation, whereas for the y momentum conservation equation we have uv and v square. So a variable appears in nonlinear form in one or more equations. So here the velocity is appearing in nonlinear form in the two equations. So there is a nonlinearity, we say. And source terms can cause nonlinearity in the fluid flow equations. Again, this is true because like source terms here also it can cause nonlinearity. So answer is option D. That is second and third statements are true. Whereas first statement it is stating that multiple variables appears in the same equation. That we call it coupling, not nonlinearity. So answer is option D. Now we'll go to question 17. In question 17, it is asked that which of the following statements is true about coupling in the context of governing equations for fluid flows. Now the question is about coupling. Previous question it was about nonlinear equations. So in this question it is about coupling. So first one, the same variable appears in more than one equation. Multiple variables appear in the same equation. Third one, a variable appears in nonlinear form in an equation. So here it is, as I said in the last question itself, the right answer is multiple variables appear in the same equation. For example, in the pressure velocity coupling, we call it coupled because in the momentum conservation equation, we have the velocity variables as well and we have the pressure term as well. So we call it a coupled equation. So answer is second statement only. We'll just look at the options first. Option A 1 only, option B 2 only, option C 1 and 2, option D 2 and 3. So answer is option B only, that is B 2 only. Because same variable appears in more than one equation, that is we do not call it as coupling, because obviously it appears when we are dealing with the R system. So we'll see the options first. It is right answer is option B. Because multiple variables appear in the same equation, that is in the x momentum or y momentum equation, we have the velocity terms and along with that we have pressure term as well. So we call it coupling in that context. I hope it is clear. Now we'll go to next question, or yeah. Question 18, we have almost how many questions? Like 25 questions are there. So 7 questions are remaining. And we have almost 45 minutes. I don't think it would take that long. So if you have any concerns, you can mention now. We can like discuss that. So I don't know why, but the count is decreasing day by day. If there are any concerns, you can just inform me. I can rectify that. Maybe today's class would be little boring because there are too many theory questions rather than problem solvings, which we have done in the previous sessions. So we'll see. Yeah, question 18. It is about advantages of beam warming method over McCormick method is similar question we have seen in previous slides also. So first one, it is applicable for viscous fluids. Second one, larger time steps can be used. A 1 only, B 2 only, C 1 and 2, D neither 1 nor 2. Answer is option B, because in the previous slide itself we have seen how McCormick scheme is conditionally stable and beam warming scheme is unconditionally stable. But both can be used for viscous fluids, and beam warming scheme, since it is a unconditionally stable system, we can use larger time step. But one must be conscious when using larger time steps, because the intermediate values would not be giving more accurate solutions. Therefore, if the our goal is to get a solution for steady state, it can be done with larger time steps. But if in intermediate time step values are required, then we must be cautious of having a larger time step. Like, we should be aware that larger time step is being implemented, and we should be checking the values and accuracy, and therefore if required we should reduce the time step level. Like, it should be done based on the requirement. So, but the advantage of beam warming scheme over the McCormick method is that larger time step can be used in beam warming method. So we go to question 19. In question 19, for the unsteady three-dimensional compressible flow, which of the following statements is true about beam warming method to find the velocity and pressure fields? Option 1, viscous term needs to be neglected. Option 2, solution of the energy equations is not necessary since we need only pressure and velocity. A 1 only, B 2 only, C 1 and 2, D neither 1 nor 2. I think it is answer D. Because for the unsteady three-dimensional compressible flows, which of the following statements is true about using the beam warming method to find the velocity and pressure fields? So in beam warming method, it is not mentioned anywhere that viscous term needs to be included. Sorry, viscous term needs to be neglected. Viscous terms can be there and it can be used. And second one, solution of energy equation is not necessary since we need only pressure and velocity. Again, it is false, because we are dealing with the compressible flows. Solution of energy equation is required. Actually, a similar question came in few slides back. There, this statement was missing actually. Is not required because it is a false. Similar statement is repeated here. So we were around question 18. And yeah, 19th question. So viscous term needs to be neglected is a false statement, and similarly solution of energy equation is not necessary is again a false statement, because since we are dealing with the compressible flows, we need the solution of energy equation as well, and viscosity term can be included. So both 1 and 2 statements are false. So option A is wrong, option B is wrong, option C is wrong, option D is the right answer, because we can say that it is neither 1 nor 2. Both the statements are false. And we go to question 20. In question 20, it is asked that which of the following statements is true about McCormick scheme. So I think these questions are kind of repeated questions, but never mind. So first one, it is about it is conditionally stable. Second, it is first order accurate. 1 only, 2 only, 1 and 2, neither 1 nor 2. As we have seen, it is conditionally stable is the only right answer. Option A is the right answer, because we all know that McCormick scheme is also second order accurate, similar to the beam warming method. So only difference is that McCormick scheme is conditionally stable. the conditional stability is given in terms of time step size. So time step delta t is should be less than or equal to delta t CFL divided by 1 plus F into delta t CFL divided by 1 plus Reynolds number divided by, or previously, just a minute, 1 plus 2 divided by RE delta, that is Reynolds number. So here we are imposing a criteria on time step size based on the Reynolds number and Courant flow delta T CFL limited. So it is conditionally stable. We need to follow the time step size based on that requirement. So first statement is only right. Option question 21. For three-dimensional incompressible flows, minimum number of partial differential equation needs to be solved is option A 3, option B 4, option C 5, option D 6. So in incompressible flows, if we consider, it is a three-dimensional system. So how many governing equations we have? First let us discuss that. We have one continuity equation, three momentum conservation equations, and one energy equation, and one, I mean not one, but species conservation equation if there are, if reactions are involved. So on that basis, how many equations now we have? If we ignore the chemical reaction, we have 5 equations. Again here it is an incompressible system, so we are not dealing with any density changes, so we can ignore the energy equation as well unless there is any temperature changes that is significantly happening in the system. So we have one continuity equation and 3 momentum conservation equations. So like x direction, y direction and z direction momentum conservation equations. So it is totaling up to 4. So answer is option B. So it is an incompressible flow system, therefore we need not solve for energy equation. If it is a compressible flow system, you need to remember that we need to solve additionally for the energy equation as well. Thereby it would be like 3 plus 1, 4 plus 1, 5. 5 equations we would be required to solve. Question 22, it is asked that which of the following is a characteristic feature of the artificial compressibility approach to solving in Navier-Stokes equations? Option 1, pressure need not be evaluated. Option 2, can be applied to unsteady flows. Third one, cannot be applied to three-dimensional flows. So artificial compressibility method is one method to solve the incompressible flows. Whereas in compressible flows we had two methods. One is explicit scheme and one is implicit scheme. So explicit scheme we use McCormack scheme, whereas for implicit scheme we use the beam-forming method. Whereas for solving incompressible fluid flow system we have 4 approaches. First is artificial compressibility, steam function vorticity approach, pressure equation and pressure correction equation. So in this question it is about artificial compressibility method. In artificial compressibility method we introduce a pseudo compressibility factor and like indirectly we assume it to be compressible forms. So the question is about which is a characteristic feature. So pressure need not be evaluated is the right answer, because the limitation of artificial compressibility approach is that it can be used only for steady state systems. So answer is option 1, that is pressure need not be evaluated, because it is an even though it is an incompressible method, like we are using artificial compressibility approach. Thereby, we are assuming a pseudo compressibility factor, introducing pseudo compressibility factor, and then doing the calculations. So, if so, we can get the pressure from the equation of state. Otherwise, we need to solve directly in the incompressible Navier-Stokes equations. So, first statement is the right statement. Let us move on to question 22. In question 22, it is asked that, okay, not question. Question 22 is just an explanation for this question. Main difficulty with the solution of incompressible flow equation is the decoupling of the continuity and momentum conservation equations due to the absence of pressure term for the former. So, in incompressible flow equation, what happens is that pressure is absent in the continuity equation. So therefore it is difficult to decouple the pressure and the velocity terms. So it is a difficulty, and Poisson equation can be used for calculating the pressure field. So given a velocity field that satisfies the incompressibility condition both inside the computational domain as well as the boundaries. So we can solve the pressure field from the Poisson equation, not I mentioned the equation of state which is false. So Poisson equation can be used for calculating the pressure field when we know the velocity field that satisfies the incompressibility condition both inside the computational domain as well as at the boundaries. Corin proposed the entirely different approach in order to overcome the difficulty of pressure decoupling. This approach is called artificial compressibility. So in general, while solving the incompressible fluid flow system, there is a difficulty encountered while decoupling the continuity and the momentum conservation equations due to the absence of pressure in the continuity equation. And this pressure can be calculated by using a Poisson equation when we know the velocity equation. This is a generalized approach. When that velocity field satisfies the incompressibility condition both inside the computational domain as well as at the boundaries. And this in order to like overcome these issues or overcome the difficulty of the pressure velocity decoupling, Corain introduced an entirely new approach called the artificial compressibility approach. And in this method, a fictitious time derivative of pressure is added to the continuity equation, so that set of equations modified from incompressible Navier-Stokes equation can be solved implicitly by marching in pseudo time. It is limited to steady state flows. So what we are doing, we are introducing a fictitious time derivative of pressure in the continuity equation. Therefore, we are solving the problem of pressure velocity decoupling. So that set of equations modified from incompressible Navier-Stokes equations can be solved implicitly by marching in pseudo time. It is limited to steady state flows. So I hope it is clear. Now we'll go to question 23. In question 23, it is asked that which of the following variables are evaluated at the same location in staggered grid. So this is a staggered grid approach. In staggered grid, we know the pressure is calculated at the centers and velocity is calculated along the boundaries, and not boundaries, cell lines or faces. So velocity is calculated along the faces and pressure is calculated at the center of the cells. So which of the following are evaluated at the same location? First, U component velocity, V component velocity, X component velocity U, Y component velocity V, and third one pressure, fourth one temperature. So the scalars are evaluated at the center of the cells and the vectors are calculated along the faces of the cells or this particular lines. I don't get the exact term now. So therefore 3 and 4 are the right answer, because even though we calculate the velocity along the faces for x and y velocity terms, you need to remember that x component is along the x direction and y component velocity is calculated along the y direction. So as you can see that V is calculated this way and X would be calculated this way. So they are not calculated at the same point. So this and this are ignored and they are not, they false for this particular question, and P and T they are scalars, so therefore they are calculated at the center of the cells. So 1 and 2 is false, 2 and 3 is again false, 3 and 4 is right answer. Option D, 1 and 4 is false. Answer is option C, that is 3 and 4. Scalars are calculated at the center of the cell. Therefore, which of the following, like they are calculated at the exactly same location in the staggered grid arrangement. In staggered grid arrangement, you need to remember that pressure or scalars are calculated at the center of the cells and vectors are calculated along the faces. So this faces, along that we calculate the vectors, and in the center of the cell we calculate the scalars. So since pressure and temperature are scalars, we calculate it at the same point. Whereas u and v component are different component velocities. U and v are x and y component velocities, so they are calculated at different points. They would be calculated in x direction and y direction separately. So they are not calculated at the same location. Even though they are calculated at phases, they differ in locations. That is for question 23. In question 24, we need to find that which of the following methods require an equation of state. So first one, stream function vorticity method. Second one is artificial compressibility method. Third one, McCormack method. So 2 and 3 is my guess. We'll see the options first. Option A 1, option B 2, option C 3, option D 2 and 3. Answer is option D, because in the first one it is a stream function vorticity approach. It is the solution method available to compute the solution for the incompressible fluid flow Navier-Stokes equation. So there, in that, I think pressure is computed from Poisson equation, I think, but not definitely from the equation of state. Whereas in the McCormack method, if you remember, it is a method to solve for the compressible fluid flow equation. So in that we solve the continuity equation and momentum conservation equation. So from the continuity equations we get rho, and momentum conservation equation we get rho u and rho v, or depending on the dimension, like 2 dimension we get rho u and rho v. And from the pressure and the temperature we need to get from the equation of state. Like in addition we solve the energy equation as well and get ET. So this particular pressure is a function of energy and the density. So we use the equation of state. Similarly, temperature is a function of rho and E. Again we use the equation of state. So McCormack method, we use the equation of state to obtain the pressure and temperature. So since artificial compressibility approach is, in that we are introducing an additional fictitious pressure term, and we are following a procedure similar to the one we use for compressibility method, compressibility flow, compressible flow, compressible flow. The need for use of equation of state arises over here. So answer is both 2 and 3. Option D 2 and 3 is the right answer. Artificial compressibility approach and McCormack method. So answer is option D. So that's it for this week's problem. So if you have any doubts, please feel free to ask now. We can discuss that now. If there is any doubts, you can ask, or if there are no doubts, we can close the session. That's it for today, this week. If you need, we can just have a quick recap of this week's session because we have a time. So we'll wait 5 minutes, and if there are no questions, we can just have a quick recap of this week's session and then we can end the session. So this week, I guess no one is there to ask question as well. So we just discuss the things and then we can close. So basically, in this week we saw about the solution of Navier-Stokes equation to the compressible fluid flow. So the problems related to that we have discussed. So we can classify the compressible fluid flow methods into two, explicit and implicit. So the one that comes under explicit scheme is McCormack method, introduced in 1969, I guess. And then implicit scheme is beam warming scheme. So in McCormack scheme, it is a conditionally stable scheme. Whereas in beam warming scheme, it is an unconditionally stable scheme. Because in McCormack scheme, we have a conditional stability which limits the time step size. Delta T should be less than or equal to delta T CFL divided by 1 plus 2 by mesh Reynolds number into some safety factor F. I mean the whole term into some safety factor F. So always the time step size should be less than that particular value. So it is a conditionally stable scheme. Whereas beam warming scheme is an unconditionally stable scheme, but it requires a calculation of intermediate evaluations in the calculations. But it can be solved implicitly, like it finally gives some equations in the tridiagonal matrix form also. And one more thing is both are second order accurate. And then what difference does it make? Like mostly the questions were covered from that. We can just go back quickly and look at it. And we saw about what is compressible flows. So many problems were about that. What is compressible flows? Compressible flows are those in which there are major density changes. How do we know when there is a major density change? We can find it out using Mach number. So if Mach number is greater than 0.3, density changes are more than 5%. So at that condition, we can say the Mach number is greater than 0.3. It is just around that. It need not be exactly 0.3 or something. We should be able to visualize that. And if it is greater than 0.3, density changes are significant. It is like greater than 5%. Therefore, the flow is compressible. Whereas if it is less than 0.3, density changes are significantly low. Therefore, we can call it incompressible flows, whereby density changes is not significant. And one more thing is compressible flow systems, we calculate continuity equation, density from continuity equation, rho u from x direction momentum equation, rho v from y direction momentum equation, energy equation for ET, and we use equation of state to obtain pressure and temperature because they are function of rho and E. So this also was asked in so many questions. So basically, if velocity is high, we call it compressible flows. Because Mach number is again a ratio of velocity of fluid, local flow velocity divided by the speed of sound in that medium. So yes, basically that's what covered in the compressible flow side. And after that, it was about coupling. And so why do we call it coupling? Because we have a presence of pressure and velocity in the same equation, we call it coupled equation. And similarly, we have non-linearity because we have uv and u square etc. in the x direction momentum equation itself. We call it non-linear equation. So these two factors poses a difficulty while solving the system, that is coupled equations, and non-linearity in the governing equation poses difficulty while solving the Navier-Stokes equation. So after that we saw about the incompressible fluid flow. Incompressible fluid flow technique. So in incompressible fluid flow technique, there are four methods. The first one is artificial compressibility method. Second one is um, stream function vorticity approach and pressure correction method and pressure uh, what is the one more method, pressure equation and pressure correction method. So in the artificial compressibility approach, we introduce an additional term like fictitious pressure correction factor to account, I mean to have the pressure in that equation as well, so that it helps in decoupling the equation. Fictitious time derivative of pressure is added to the continuity equation, so that set of equations modified from the incompressible Navier-Stokes equation can be solved implicitly by marching in pseudo time, but it is limited to steady state flows. So that is one, and this is just an introduction to the incompressible fluid flow techniques. And there is one more thing, that is like pressure velocity calculation from the staggered grid for pressure correction method, I guess. So here we calculate the scalars at the center of cells and vectors at the faces of the cells. So pressure, temperature, etc. will be calculated from the center, whereas velocity would be calculated all of the faces, and it depends on the face, side of the face or edges. Yeah, like in two dimension both are same. Yes. So this is known as staggered grid approach, where there is a different point for calculation of the pressure and the velocity. So in pressure equation method, we use the staggered grid. So like, why do we go for staggered grid is that there would be fluctuations, like in when we go for the pressure variation, pressure gradient, and like sometimes it might become zero, therefore the fluctuations would be there in the final solutions. So to get rid of the fluctuation in the final solution, when we solve pressure, mm, at different points than the vectors. So one more thing that can be done is, instead of the cells we can use this edges for pressure calculation also, and this for the velocity calculations. So basically it depends, but uh, generally like scalars at one point and vectors at different points, if you remember it shortly. So only to get rid of the fluctuation in the solution, we use the staggered grid method. So pressure and temperature is the answer. So that's it for today's class. If there are any doubts, you can ask, or else we'll close the session. So no one is there basically. So I think we can close the session. I thank everyone for attending this week. Okay. So if there are any feedback, you can mention in the video. Like these videos are available for in the YouTube as well for your understanding. Like you can view that later, and if there are any doubts, you can mention there. I can see that and I can give suggestions for that. Or if there are any mistakes on my part, I can correct it as well, and I can let you know in the next week's session, or I can put it there as well, whichever is convenient. So like that's all for today's session. We can close today's session, and like we can meet again the next week. I hope that week it would be more interesting and you people would be more interested to join as well. So guys, thank you. I'm closing the session now. Yeah, thank you. Like please let me know the feedback if you have any, so that I can improve myself, and I can help you as well in that process. Thank you guys. Thank you.